In the first months and years of World War II, strategic bombing emerged as a decisive form of modern warfare. By 1943-1944, the Allies had demonstrated the destructive potential of long-range, high-altitude bombers operating with heavy payloads and integrated avionics. For Germany, the strategic situation changed dramatically as the war shifted onto multiple fronts, and air raids over the Reich became increasingly frequent. German military planners and aircraft designers faced a stark set of realities. The Luftwaffe's initial focus had been tactical air support for fast, maneuvering ground operations. What it had not prioritized was a stable, mature heavy bomber force able to carry large strategic loads over intercontinental distances. Yet by the middle of the war, a thread of projects emerged that specifically aimed to produce a bomber with the B-29 Superfortress's key capabilities: long-range, heavy payload, high operational altitude, advanced crew accommodations such as pressurization, and complex defensive systems. Understanding why German scientists and engineers pursued B-29-like performance requires looking at strategic motivations, industrial constraints, and a set of technical temptations that cut across doctrine and desperation. Strategically, the B-29 represented a new class of strategic weapon, an aircraft optimized for long-range, sustained bombing runs against industrial and civilian targets, equipped with innovations aimed at crew endurance and precision. The B-29 was designed to operate at higher altitudes, to deliver heavier payloads over greater distances, and to employ remote-controlled defensive armament linked to centralized fire control computers. For German planners, the prospect of an American fleet of such bombers threatened the homeland in ways that earlier bomber models did not. The reaction in Germany was twofold. First, a desire to counter these Allied bombers in the air and on the ground with better fighters and anti-aircraft defenses. Second, a parallel effort to field a bomber capable of retaliatory strategic strikes, or at least of projecting force over longer distances. The latter thinking underpinned the so-called America bomber concept, an aspirational program to create aircraft capable of reaching the continental United States from bases in occupied Europe or the Azores. Even if that particular ambition was never realized operationally, it drove German engineering toward large, four-engine designs that shared architectural goals with the B-29. Industrially, German aviation in 1943-1944 was constrained by several interlocking problems: shortages of high-octane fuel, limited access to advanced alloys and production capacity, and bottlenecks in engine development. The Luftwaffe's heavy bomber programs were hindered by repeated priorities shifting toward fighters. Nevertheless, individual companies and research groups possessed significant engineering talent and had produced technically advanced designs, sometimes over-ambitious relative to wartime realities. This mismatch between ambition and industrial reality is crucial. German scientists could study Allied successes on paper and try to replicate their features, but the replication required reliable, mass-producible components: engines, turbo-superchargers, long-endurance airframes, and advanced electronics that Germany increasingly lacked by mid-war. Technically, what the Germans admired and tried to copy from the B-29 boiled down to several discrete features: robust four-engine layouts optimized for high power and range, pressurized crew compartments to allow comfortable high-altitude flight, remote-controlled gun turrets to slim down crew workload and aerodynamic drag, and systems integration that combined engine performance, fuel capacity, and structural strength into an airframe capable of sustained long-range missions. The B-29's Wright R-3550 engines, its pressurized cabin, its centralized analog fire control system, and its aerodynamic refinement were not easy to match. Still, German engineers attempted to reproduce comparable solutions through their own technology set, sometimes converging on the same engineering choices, sometimes taking different routes born of local strengths or supply constraints. An important historical point. Germany rarely, if ever, had direct access to intact B-29 airframes for reverse engineering. The B-29 entered service late in the war and operated primarily in the Pacific theater. Germany's intelligence and technical collection instead relied on reports, captured fragments of Allied aircraft, and extrapolations from known Allied design philosophies. That meant German attempts were often derivative, hybrid, or speculative, and based on the assumption that the core ideas, high power, pressurization, long wingspans, could be implemented with German components. The challenge was twofold: to understand what made the B-29 work, and to find German engineering equivalents that could deliver the same performance under wartime production conditions. Psychologically and culturally, German aircraft designers carried both pride and frustration. The pre-war years had produced advanced designs, such as the four-engine Door-X seaplane in the interwar era, and a number of cutting-edge prototypes. But wartime exigencies and a doctrinal bias favoring tactical air power meant that heavy bomber programs were underdeveloped and frequently sabotaged by shifting directives and resource rationing. When the B-29's feats, especially later in 1944-1945, became known, they were read through a lens of what-ifs. What if Germany had pushed harder earlier for a strategic bomber? What tools would have been needed? German scientists and technical leaders did not merely want to copy the B-29, they wanted to understand the design principles that allowed it to perform, and to adapt those principles to German industrial realities. That mixture of engineering curiosity and strategic necessity drove the technical attempts discussed in the next section. To anchor this context with examples, the America bomber competition resulted in designs such as the Messerschmitt Me-264, the Junkers U-390, an enlarged descendant of the U-290, and proposals from Heinkel and others. These projects were German efforts at long-range designs of heavy bombers capable, on paper, of ranges comparable to the B-29's. At the same time, existing German heavy bomber programs, such as the Heinkel HE-177, were being retrofitted or reimagined to solve the same set of technical challenges the B-29 had addressed from the outset: engine reliability under sustained power, crew ergonomics for long flights, and systems integration for navigation and defensive fire. These projects provide concrete examples of the intersection between German aims and B-29-like features. The Messerschmitt Me-264's proposed fuel load and range ambitions, the Junkers U-390's enlarged wing and fuselage to carry greater payloads, and Heinkel's experiments with high-altitude pressurization on the HE-274 prototypes. Finally, the political layer is unavoidable. By 1944, Germany faced a multi-front collapse and growing Allied bombing campaigns. High command oscillated between throwing resources at miracle weapons and making pragmatic decisions that favored immediate tactical needs. The long-term, resource-heavy technological investments required to produce a practical B-29 equivalent were therefore always at risk. That political volatility shaped not just procurement, but also the morale and focus of scientists and engineers. They knew the constraints, but many pursued engineering excellence as a matter of professional honor and intellectual curiosity, producing prototypes and reports that later historians would analyze as half-finished answers to the question, could Germany have built a true B-29 equivalent? The answer the technical record gives, complicated and layered, will occupy the next part of this script.
When engineers set out to replicate or emulate an existing aircraft's capabilities, they often face the paradox that copying outward features, wingspan, engine count, or fuselage size, does not guarantee the underlying performance unless the integrated systems match. The B-29's success was not merely its four engines or its pressurized cabin. It was the result of a coordinated set of components working together: reliable high-power radials, robust cooling systems, adequate fuel capacity in structurally efficient wing tanks, digital-era equivalent fire control, analog computers, and an airframe tuned for high-altitude cruise. German efforts splintered into multiple approaches. Some sought to build a similar heavyweight from first principles. Others tried to adapt existing designs, and many pursued hybrid experiments to overcome specific deficiencies in engines, defensive armaments, or crew habitability. One major axis of German choice involved engines. The B-29 used the Wright R3350 duplex cyclone radial engine, a high-power power plant that, once its early teething problems were managed, delivered the performance needed for heavy, high-altitude cruise. German industry, by contrast, faced a thorny engine problem, a shortage of reliable, high-power engines for large airframes. Early German attempts to get the required horsepower led to engine coupling, the practice of pairing two engines closely to drive a single propeller gearbox. The Daimler-Benz DB606 and DB610 were effectively twin DB601 or DB605 engines bolted together. The Heinkel 177 Greif originally used coupled engines to reduce frontal area and improve streamlining, but the result was a cascade of problems: overheating, lubrication failures, and an alarming tendency for the coupled units to catch fire. The Heinkel 177's engine issues became infamous. In practical terms, they showed the limits of coupling under the thermal and operational stresses of sustained high-power flight. In comparison, the B-29's approach, dedicated single high-power engines for each nacelle, avoided coupling complexity and allowed engines to be developed with more predictable cooling and maintenance characteristics. To replicate B-29 range and payload, German designers explored alternatives. One route was to enlarge existing four-engine designs. The Junkers U-290 and later conceptual derivatives, the U-390 and the U-390's ancestor series, were part of this approach. The U-290 had already demonstrated considerable range and payload, operating in maritime patrol and transport roles. The U-390 was an attempt to scale that concept into the America bomber role. Its projected range figures were ambitious. Some calculations claimed potential ranges approaching those required to reach the eastern seaboard of North America from Western Europe if operating from forward bases. The engineering trade-offs were clear. To achieve such ranges, you needed larger wing area, more fuel, and robust engines, plus structural reinforcement to bear heavier loads. But expanding airframe size only magnifies other issues: stress on landing gear, increased takeoff distance, and more severe engine cooling demands during climb. The B-29's designers built a new airframe from the outset with these requirements in mind. German attempts often retrofitted or scaled pre-existing designs, creating compromises. Pressurization presented another engineering frontier. The B-29's pressurized cabin was a major innovation for crew endurance and operational capability at higher altitudes. German engineers were familiar with pressure cabins. The Heinkel 274 prototypes, for instance, were designed specifically for high-altitude operations with pressurized compartments. But pressurization only works when the aircraft's fuselage, hatches, windows, and seals are engineered to maintain differential pressures reliably over thousands of hours of operation. Achieving this required materials understanding, manufacturing precision, and systems redundancy. Germany could produce pressurized prototypes, but doing so at scale across dozens or hundreds of airframes under wartime production constraints posed significant difficulties. The B-29's production itself was a costly, technically demanding enterprise, involving massive retooling and factory specialization. Expecting Germany to replicate that scale in the late war period was unrealistic.
Defensive armament and fire control were another area of divergence, where copying became one of reinvention. The B-29's remote-controlled turrets, operated by central gunnery stations with analog predictors, reduced drag and allowed for more efficient spacing of crew roles. German engineers experimented with remote turrets as well. These systems had earlier precedent in German designs, but integration with radar, aiming computers, and redundant power supplies was complex. Where the Allies had invested heavily in systems-level engineering for long-range escorts and bomber survivability, German development often produced novel mechanisms that lacked the required electronics integration or combat-proven reliability. For example, the Heinkel HE-177's defensive layout and slow-responding systems could not match the B-29's range of centralized fire control. Additionally, the Luftwaffe's doctrine continued to emphasize fighter interception as the primary defense, meaning bomber defensive systems did not receive the same industrial focus. A recurring technical story in German attempts was the problem of cooling and engine reliability. High-power radials and inline engines running at sustained high power produce intense heat. American engine makers developed cooling strategies and maintenance practices oriented toward long missions. German coupling techniques, while aiming for aerodynamic advantage, created concentrated heat sources that were harder to ventilate. The R-3350 had its own early issues. American crews suffered engine fires in the Pacific in 1944, but mass production and iterative fixes gradually improved reliability. Germany, suffering resource shortages and intermittent testing opportunities, often produced engines that could not be perfected in time or that behaved unpredictably when pushed to the power settings needed for B-29 level operations. Beyond engines, fuel logistics mattered. The B-29's design relied on a fuel infrastructure and supply chain that prioritized long-range bombers. German ambitions to reach similar ranges ran into practical logistics, fuel types, availability of long-range tanker support, which the Luftwaffe did not have, and the need for forward bases that were politically and militarily viable. Without secure forward bases or carrier-equivalent staging points, the theoretical range of a bomber is only as useful as the surrounding logistical support. German planners sometimes proposed using bases in the Azores or captured airfields in the Soviet Union, but these options were fragile and contested. Material science and production tolerances also played a role. The B-29 benefited from American industrial capacity, which could supply consistent alloys, rivets, and machining standards at scale. German factories, under bombing pressure and raw material shortages, often substituted lesser alloys or produced components with variable tolerances, which reduced airframe longevity and reliability. High-altitude pressurization, for instance, stresses fuselage's joints in ways that demand tight tolerances and corrosion-resistant materials. Germany's ability to maintain that standard across a production run was limited in the late war period. Specific projects illustrate these themes with concrete detail. The Messerschmitt Me-264, an elegant, long-range design, showed that German firms could conceptualize aircraft with ranges approaching those needed to cross the Atlantic. But the Me-264 remained a prototype with few airframes built and did not overcome the engine or production scaling challenge. The Heinkel HE-274, developed in Vichy, France, and later captured and finished post-war by the French, demonstrated pressurization and high-altitude capabilities in prototype form, but never entered mass production. The Heinkel HE-177, as mentioned earlier, embodied the engineering costs of wrong choices. Its coupled engines created persistent reliability problems. The Junkers UE-390, a stretched Ju-290 derivative, flew as an experimental long-range platform and was used for transport and reconnaissance trials, but it lacked the robust systems integration and production support to become a strategic bomber on the scale of the B-29.
In performance comparisons, the B-29 generally outpaced German equivalents in operational cohesion. The Superfortress combined a reliable engine suite, after fixes, and airframe built to handle long, high-altitude flights, extensive crew systems, and a production system capable of producing large numbers relatively quickly. German designs often matched one or two of these criteria on paper, range here, pressurization there, but rarely integrated all of them together with the industrial backbone necessary to make the concept operational. Consequently, German copies of B-29 attributes were usually partial. German aircraft might equal or exceed the B-29 in a narrow metric range on a specific prototype flight, for instance, but not across the whole spectrum of requirements for strategic operations. This fragmentation of effort and the repeated failure to integrate components into a mass-producible whole were perhaps the most significant practical differences. The B-29 succeeded not because it excelled in a single domain, but because the United States could align industrial power, engineering iteration, logistical support, and doctrine toward a common, achievable goal. German scientists and engineers produced remarkable individual innovations and prototypes. Their experiments influenced post-war aviation and provided valuable technical lessons. But when measured against the B-29, not as a singular object, but as a strategic system, the German attempts fell short in systemic terms rather than in individual ingenuity. By late 1944 and 1945, the gap between German ambition and operational reality had become painfully clear. None of the German long-range bomber projects, the Me-264, Ju-390, H-177 modifications, or H-274 prototypes, translated into an operational fleet capable of performing B-29-style strategic bombing. Yet the story does not end with failure. Rather, it produces a set of technical lessons, personnel transfers, and post-war impacts that shaped aviation development in Europe and beyond. This concluding section examines what German scientists and engineers learned through their attempts to copy B-29 features, how those lessons migrated into post-war programs, and what the broader implications were for aviation engineering. First, the operational consequences during the war were practical. Germany did not develop a strategic bomber force to challenge Allied long-range operations. The Luftwaffe remained primarily a tactical air force, and strategic bombing tasks fell to the Allies. The lack of a German B-29 equivalent meant Germany could not retaliate against the United States' industrial heartland, nor could it mount sustained intercontinental campaigns. Instead, the strategic bombing war was played out over Europe at shorter ranges, with the Luftwaffe on the defensive. That asymmetry contributed to the cumulative pressures on German war production and civilian morale. From a technical lessons perspective, several key takeaways emerged from German projects. The first was the value of systems integration. Engineers repeatedly discovered that engines, airframe, fuel systems, pressurization, and electronics had to be developed in tandem. Solving one problem in isolation often exposed another. The HE-177's engine fires taught a blunt lesson about engine layout choices. Compacted power plants might save drag, but could create catastrophic failure modes. Post-war designers in both Germany in later decades and elsewhere took these warnings seriously, favoring more maintainable engine installations and improved cooling and lubrication design. Second, the experiments with pressurization and high-altitude flight had a lasting technical payoff. Even limited prototypes like the HE-274 demonstrated that German teams possessed the theoretical and manufacturing ability to build pressure cabins. That knowledge, how to shape fuselage sections, how to seal hatches and design pressure bulkheads, fed into post-war aerospace work. Engineers who survived the war and later joined Allied or neutral nation projects carried this know-how into jet-age bomber and transport designs. Thus, while Germany did not field a B-29 during the war, the technical groundwork contributed to later progress in high-altitude aircraft.
Third, the defensive systems and remote turret experiments provided insight into human-machine interaction at scale. The B-29's centralized fire control demonstrated an effective way of reducing crew workload while improving accuracy. German experiments in remote weapons control, although not mature, radar and electronic warfare, areas where the conceptual seed had been planted during wartime engineering trials. The human capital consequences were also significant. Many German scientists and engineers were captured, recruited, or emigrated after the war,
under programs such as Operation Paperclip. The engineering knowledge about large airframes, engine designs, and high-altitude systems contributed to Allied programs in the United States, the United Kingdom, and the Soviet Union. In the case of the United States, wartime study of German concept work helped refine designs for jet transports and strategic aircraft during the early Cold War. Conversely, the Soviet Union also benefited by appropriating German technical data and personnel to help bootstrap its own post-war bomber and jet programs. There are ethical and historical nuances to consider as well. The technological chase to match or exceed an enemy's weaponry can drive innovation, but it also reflects how wartime priorities can divert resources from other needs. Germany's late war investment in exotic aircraft and wonder weapons drew criticism both during and after the war for diverting scarce resources. The B-29 comparison highlights a deeper question about strategy. Was emulating enemy technology the right path, or should resources have been concentrated on more immediately effective defenses? Retrospective analysis suggests that Germany's fragmented investment across many ambitious projects reduced its capacity to achieve decisive breakthroughs in any single area. For modern audiences, especially an American audience familiar with the B-29's role in symbolism, the German attempts offer a cautionary tale and a technical drama. They show how engineering ingenuity can collide with political, industrial, and logistical realities. They demonstrate the complexity of translating a conceptual capability into operational reality under wartime constraints. At a human level, the story is also about the engineers who pursued excellence in adverse conditions. Their persistence produced prototypes, flight tests, and engineering reports that became stepping stones for post-war aviation. A balanced final assessment recognizes both the technical creativity present in German programs and the systemic reasons they failed to produce a B-29 equivalent. Technically, German scientists invented, tested, and sometimes fielded advanced subcomponents, pressure cabins, long-range airframe concepts, and experimental remote weapons. But operationally, the combination of engine unreliability, especially from coupled engines, shortages of materials and fuel, production disruptions from strategic bombing, and doctrinal ambiguity made the mass production of a practical B-29 class bomber unachievable. In comparison, the United States marshaled industrial capacity, standardized production practices, and iterative refinement in the field to convert the B-29 from prototype to strategic weapon. Finally, the legacy of these attempts extended into the Cold War and the jet age. Engineers who had wrestled with long-range flight and pressurization applied that experience to post-war transports and jet bombers. The design trade-offs, engine arrangement, aerodynamic cleanliness versus maintenance accessibility, the cost of technological integration remain central themes in aerospace engineering. For historians and aviation enthusiasts, the German attempts to replicate B-29 features are a rich subject precisely because they combine clear technical ingenuity with stark operational failure. The contrast ultimately highlights a lesson often overlooked in technical admiration. Successful weapon systems are as much about industrial capacity, logistics, and doctrine as they are about individual design breakthroughs.